Depth-First Search (DFS) is a systematic way of exploring every vertex and edge of a graph by moving as far as possible along each branch before backtracking. Formally, given a graph G equals V, E and a start vertex S in V, DFS produces a traversal order, a sequence V sub 1, V sub 2, V sub vertical bar, V vertical bar, such that each vertex is visited exactly once. The order is defined by a pre-order, the moment a vertex is first discovered, and a post-order, the moment the recursive call for that vertex finishes. An easy analogy is a maze explorer who always chooses the leftmost unexplored corridor, walks as deep as possible, and only when there is no way forward, steps back to the last junction to try another direction. This deep-first strategy guarantees that all reachable vertices are eventually visited, and the exact sequence depends on the rule used to pick the next neighbor. For example, alphabetical order, numeric ID, and so on. Explanation: the recursive version of depth-first search mirrors the mental picture of the explorer. A function DFS open parenthesis V close parenthesis marks V as visited, then recursively calls itself for each unvisited neighbor. The pseudocode is DFS-recursive open G, V close colon visited open bracket V close bracket becomes true for each U in edge open G, V close bracket. If not visited open U close bracket, then DFS-recursive open G, U close bracket. The base case is the condition if visited open bracket V close bracket. When a vertex has already been explored, the function returns immediately, preventing infinite loops on cycles. The recursion stack implicitly stores the path from the start vertex to the current vertex, so the algorithm naturally backtracks once all neighbors of a vertex are processed. This version is concise and easy to understand, but it relies on the language's call stack, which may overflow for very large graphs. Real-world analogy: think of a family tree where you ask each person to list all their children, then each child repeats the question for their children, and so on until someone has no children, the base case. When recursion depth is a concern, depth-first search can be written iteratively using an explicit stack data structure. The stack holds vertices that still have unexplored neighbors, mimicking the call stack. Depth-first search iterative of G, S colon. Stack gets assigned to empty stack, stack.push S while not stack empty colon. Vertex V gets assigned to stack pop, if not visited of V colon. Visited of V gets assigned to true first time we see V pre-order, for each U in adjacency of G and V in reverse order colon, if not visited of U colon. Stack push U, push neighbors so the leftmost is processed first. Reverse order of neighbors ensures the same order as the recursive version, when using a last in first out stack. The visited check occurs after popping, because a vertex may be pushed multiple times from different parents. The stack can be an array, list, or language-provided stack class. Its size never exceeds V because each vertex is pushed at most once per incident edge. Analogy: imagine a stack of books where each book represents a city to explore. You pull the top book, mark the city as visited, then place all its neighboring city books on top of the stack. You always work on the most recently added city, which forces you deeper into the network before you turn back to earlier books. The complexity of depth-first search depends on how the graph is stored. Adjacency list: for each vertex we store a list of its outgoing edges. The algorithm scans each adjacency list once, so the time is big O of V plus E, the space is big O of V for the visited array plus big O of V for the recursion stack or explicit stack, giving big O of V extra memory. Adjacency matrix: a V times V Boolean matrix tells whether an edge exists. The algorithm must examine every entry of a row to find neighbors, leading to big O of V squared time, even if the graph is sparse. The extra space is big O of V squared for the matrix plus big O of V for the stack or visited array. Edge list: less common for depth-first search because finding neighbors requires scanning all edges each time, costing big O of V times E, hence adjacency lists are preferred. In all cases, the stack depth never exceeds the number of vertices in the connected component being explored, guaranteeing linear space with adjacency lists. Real-world example: navigating a city's road map stored as a list of intersections, which are vertices, and streets, which are edges, is fast because you only look at the streets directly leaving each intersection. Storing the map as a giant grid, which is a matrix, forces you to check every possible street, even the ones that do not exist, which is wasteful. During depth-first search, We can label each traversed edge according to the relative discovery times of its endpoints. Let D of V be the discovery pre-order time of vertex V and F of V, its finish post-order time. Tree edge, edge U to V where V is discovered for the first time from U, these edges form the depth-first search forest. Back edge, edge U to V where V is an ancestor of U in the depth-first search tree. That is D of V less than D of U less than F of U less than F of V. The presence of a back edge indicates a cycle in a directed graph. Forward edge, edge U to V where V is a descendant of U but not a tree edge. That is D of U less than D of V less than F of V less than F of U appears only in directed graphs. Cross edge, edge U to V where U and V belong to different subtrees, and neither is ancestor of the other. That is F of U less than D of V or F of V less than D of U. These classifications are useful for cycle detection. In an undirected graph, a back edge ignoring the trivial edge back to the parent directly signals a cycle. In a directed graph, any back edge means a directed cycle exists. The algorithm simply checks during edge exploration whether the neighbor is already visited, and whether its discovery time is earlier than the current vertex's discovery time. Analogy: think of a family genealogy where tree edges are parent-child links, back edges are marriage within the family, a cousin marrying a cousin creating a loop, forward edges are grandchild shortcuts, and cross edges are connections between two distant branches. When the input graph is not connected, depth-first search does not stop after the first component. Instead, it starts a new depth-first search call from the smallest unvisited vertex, creating a DFS forest, a collection of DFS trees, one per component. The algorithm recursive version looks like: for each vertex V in capital V in sorted order, if not visited V, DFS recursive GV, this builds a new tree in the forest. Each tree records the discovery/finish times for vertices in that component only. The forest lets us answer questions like how many connected components does the graph have? Simply count how many times the outer loop initiates a DFS call. Real-world analogy: imagine a group of explorers each standing on separate islands, connected components. Each explorer explores the land reachable from his island, a tree. When all explorers have finished, we have a map consisting of several separate trees, the forest. DFS is a building block for many higher-level graph algorithms. Topological sorting for a D of G. Perform DFS, then list vertices in reverse order of their finish times F of V because every edge U, V in a D of G satisfies F of U greater than F of V. The reverse list respects all dependencies. This is analogous to scheduling tasks where you must finish all prerequisites before a task begins. Strongly connected components SCCS. Kasaraju's algorithm runs DFS twice. First, DFS on the original graph obtains a list of vertices ordered by decreasing finish time. Then DFS on the transpose graph edges reversed processes vertices in that order. Each DFS tree in the second pass is an SCC. The intuition is that the first pass records a peeling order that ensures we always start a new DFS from a vertex in a sync SCC of the original graph. Other uses: detecting bridges and articulation points, solving puzzles like mazes, and performing binary decision diagrams. Mathematical note: in a D of G, the finish times give a linear extension of the partial order defined by the edges. The correctness of depth-first search hinges on the discovery/finish time invariant colon for any edge U, V. Exactly one of the following holds. 1. D of U less than D of V less than F of V less than F of U. V is a descendant of U, tree, or forward edge. 2. D of V less than D of U less than F of U less than F of V. U is a descendant of V, back edge in directed graphs. 3. F of U less than D of V or F of V less than D of U. U and V are in different depth-first search trees, cross-edge. These three mutually exclusive cases can be proved by induction on the recursion depth. The base case, first vertex, trivially satisfies the invariant. Assuming it holds for all vertices discovered before U, when exploring an edge U, V, we consider whether V is unvisited, tree edge, or already visited. The timestamps guarantee that the relative ordering cannot be violated, establishing the classification theorem. For topological sorting, the proof uses the fact that in a directed acyclic graph there are no back edges. So for every edge U, V, we have F of U greater than F of V sorting vertices by decreasing F. therefore yields a linear order consistent with all edges. For Casaraju's strongly connected component algorithm, the key lemma states, if there is an edge from component C1 to component C2 in the original graph, then the maximum finish time of any vertex in C1 is greater than that of any vertex in C2. This follows from the discovery/finish invariant and ensures that the second depth-first search, run on the transpose, starts with a vertex in a source component of the component graph, thus isolating one strongly connected component at a time. These proofs provide a solid mathematical foundation for why the intuitive go deep, then backtrack procedure works for complex tasks. Explanation:"Typical exam questions test both conceptual understanding and ability to implement depth-first search. Write pseudocode for recursive depth-first search and explain why a visited check is necessary. Strategy: write the 3-line function, highlight the base case, and discuss infinite recursion on cycles. Trace execution on a small graph example 5 vertices. Strategy: maintain a table of discovery finish times, show the stack content after each step, and identify tree back-forward cross edges. Detect a cycle in a directed graph using depth-first search. Strategy during depth-first search: if you encounter an edge to a vertex that is gray, discovered but not finished, report a cycle. Compute a topological order of a directed acyclic graph. Strategy: run depth-first search, record finish times, then output vertices in reverse order. Prove the order respects all edges. Find strongly connected components with Casaraju's algorithm. Strategy: explain the 2 passes, why we need the transpose graph, and how the finish time order guarantees correct component extraction. Complexity analysis: given adjacency list and adjacency matrix representations, compute time and space. Strategy: write big O of V plus E versus big O of V squared and justify. Edge classification: given timestamps, classify each edge. Strategy: apply the 3 inequalities from the edge classification theorem. For each type, practice by hand on a sample graph before writing code. Remember to comment your code with the meaning of gray, white, and black colors, unvisited, discovered, finished. This helps avoid logic errors during exams.